Switchable magnetic blocks don't magically turn magnetism on and off. They manipulate a permanent, constant magnetic field. When flipped on, an internal magnet rotates, aligning its poles with the ferrous casing. This extends a magnetic loop through the V-groove to grip the part. Switched off, it rotates 90 degrees across non-ferrous shields, collapsing the loop inside the block to remove all pole. Because this holding force relies on completing a magnetic circuit, the tool requires a ferrous workpiece. Materials like aluminum, brass, and copper, or solid plastics won't trigger the holding force. If your workshop frequently handles these non-ferrous materials, you cannot rely on magnetism. A mechanical standard clamp is your only viable option. Magnetic blocks don't create holding force in a vacuum. They rely entirely on the material properties of the workpiece. For a fabricator dealing with mixed materials, it is an imperfect solution. When the material is right, the magnetic block offers a massive workflow advantage. You get 100% unobstructed access to the top and sides of the cylinder. Inspectors can easily drop in dial indicators. You can gently spin a shaft to check concentricity without ever bumping into a top cramp. That delicate inspection work is very different from the violent forces of heavy milling. Under high lateral milling forces, the magnetic grip will fail. A heavy cutting tool will overpower the magnetic circuit and cause the part to slide mid-cut. Firmly, for aggressive machining tasks, you need an absolute guarantee that the part won't move. The brute force lock of a mechanical clamp provides that guarantee. Magnetic blocks are optimized for measurement visibility and speed. Standard clamped blocks are optimized for immovable rigidity. Beyond how the block holds the part, we must consider the tool's physical dimensions. If you try to hold a long or heavy shaft in a standard 2-inch block, the short base creates a pivot point. That leads to wobble and deflection at the ends. This diagram compares a 2-inch block with a larger 4-inch model. The 4-inch block doubles the contact surface area and significantly increases the moment of inertia. The downward forces are distributed over a wider base, reducing overhang leverage and eliminating vibration. Many of these larger blocks also feature a double-sided V design. You get a large groove cut into the top and a smaller groove on the bottom. This dual geometry lets a single tool adapt to the job. You can flip it over to securely grip tiny pins or use the main side for large bar stock. Investing in a 4-inch double-sided block increases your upfront cost, but it eliminates the need to buy multiple specialized blocks, compounding the versatility of your shop. There is an invisible downside to magnetic blocks. They act as a magnet for workshop debris. During normal operation, tiny metal shavings, filings, and swarf will aggressively stick to the sides and faces of the block. This forces you to adopt strict wiping and brushing protocols before you seat a new part. A single metal chip trapped in the V-groove will destroy micrometer-level accuracy. You also have to manage the magnetic field itself. Strong magnets pose a direct hazard to sensitive workshop electronics, digital storage media, and pacemakers. Even putting the tool away requires care. When storing multiple magnetic blocks, use non-ferromagnetic dividers to keep them from snapping together, which causes surface chipping and complete demagnetization. You gain rapid setup speed by ditching the top clamp, but you pay for it with the strict hygiene and safety protocols required to maintain it. So,